October 24th, 1942. El Alamein, Egypt, British Sherman tank crews were about to find something their German enemies could never figure out. The math was hard and simple. If you see a German Panzer 1,000 yards away, you stop your 32-ton tank. You wait for it to stop shaking, you aim your gun, then you fire. It takes about 4.2 seconds, and in tank fights, the crew that shoots second never makes it home. Every army in the world, German, British, Soviet, and American followed the same strong rule. If you shoot while moving, you waste shells. The tank shakes, the barrel moves up and down, and you miss targets, past 200 yards. The tests at Aberdeen, proving ground, showed it clearly. Moving tanks hit less than 10% of their shots. But then, something crazy happened. Some British Sherman crews, still driving 8 miles an hour, fired their 75mm guns and hit German tanks that were not moving at all. The German Panzer crews never expected it. They had stopped to aim just like their training said, but they were destroyed before their gunners could line up the shot. German intelligence reports later noticed strange accuracy from American tanks that fired while moving. What they didn't know was that a 34-year-old Westinghouse engineer named Clinton Hanna had broken the oldest rule in tank fighting. And the thing that did it weighed less than 300 pounds, the deadly math inside tank. Battles was simple, and by 1939 every army had written it in their books, with lessons paid in blood. A tank moving across open ground at 12 miles per hour was always shaking. The hull bounced on rough dirt. The springs pushed and pulled the whole tank, rocked like a boat in waves. Put a 9-foot-long gun barrel weighing 1,500 pounds on that shaking tank. And the result was clear. You could not hit past 200 yards. The gun moved, the sights jumped, and the target slid out of view with every bump. Tests at Aberdeen in Maryland proved what everyone already knew. Tanks that fired while moving at 300 yards hit less than 10% of the time, and at 800 yards, they hit less than 5%. The numbers were not guesses. They came from hundreds of tests with many crews, tanks, and weather. The truth was clear, and every army knew it. Every nation that had tanks in 1940 followed the same plan. Move, stop, shoot. Then, move again. This was not just a tip. It was the only way to stay alive. It came from the wrecks of tanks that tried to shoot while moving and got destroyed. British tank crews learned this the hard way in France in May 1940. When they charged and fired while driving, they missed every shot and showed the enemy where they were. The smart crews followed a harsh rule. See the enemy, stop, wait 3 to 5 seconds till the tank stops shaking. Let the gunner aim and shoot. Then move fast before the enemy fires back. Those few seconds of waiting were the cost for a real hit. Every army said the same thing. The Germans said it. The British said it. The Soviets said it. And when the United States made Field Manual 1712 in 1941, it said the same. The tank will move, stop fire, then move again. This was not advice from people who never fought. It came from real battles and what tanks could or could not do. The real pain of this rule showed in the words of American crews who fought in the hot deserts of North Africa, where M3 Lee tanks met German tanks for the first time. Their stories were broken, told by tired men still trying to understand what they had lived through. But their fear was clear. You see, the enemy tank. One man said, his hands shaking. You yell at the driver to stop. You shout at the gunner to shoot faster, and you pray that your guy fires before theirs. Another commander said, "The fear is like math. The German Panzer IV has a strong 70, 5mm gun. At 1,000 yards, it can cut through our armor like paper. We have to stop to shoot back. That gives them 4 or 5 seconds to aim at us. You keep doing that math, and someday you are the one who never moves again." This was a problem for all armies, but it became a big worry for the United States. In 1939, everyone knew war was coming, and America's tank force was small, weak, and old. The Ordnance Department, which built tanks, knew they were behind. The Germans had crushed Poland, the British and French were changing their tank plans while fighting. The Soviets had real war experience from battles with Japan. America had only training and guesses. So the Ordnance sent a request to Westinghouse. That year the message was short and clear. Make a system to keep the tank gun steady while driving on rough ground at speeds up to 15 miles per hour. No design ideas, no hints, just the goal and a deadline of 18 months. The contract value was secret, not because the money mattered, but because saying you wanted to fix this told enemies you thought it could be fixed. The penalty for failure was not written down, because people expected failure. Every big army had studied gun stabilization, and each one found it could work in theory, but was nearly impossible in real tanks. Gyroscopes were real, and ships used them. Servo systems and aircraft autopilots existed, but putting those parts into a 32-ton fighting vehicle was a different level of trouble. The tank would be driven by young soldiers across North African deserts and European mud fields, and fixed by mechanics with little technical training, and it had to work in temperatures from -20 to +120 degrees Fahrenheit, and absorb the shock of enemy hits, the recoil from firing, and the constant vibration of engines and tracks. The engineering problems were not just hard, they piled up. Each solution made new problems. Clinton Hanna got the job because he knew precision control systems, and at 34, he had a reputation for patient, steady work, not sudden big breakthroughs. He had worked on naval fire control where gyros kept guns stable on rolling ships, and he understood servo systems that could sense motion and push back faster than a person. But a tank was a different animal. Ships roll in predictable ways, and aircraft move in three-dimensional space, where control surfaces can help. A tank bounced over the ground in chaotic motion, random bumps, sudden drops, sideways, lurches from track throws, violent recoil from the main gun. The gun itself was huge, a 75mm barrel 9 feet long, and the whole assembly weighed about 1,500 pounds, and it could lever forward from the turret. The task was to keep that heavy gun steady while the vehicle below it bucked and heaved, and the whispers started right away. Ordnance officers called it a crazy project. Tank crews who heard rumors ignored it completely. One more hard thing to fail when you need it most. Even inside, Westinghouse senior engineers shook their heads. Gyroscopes belonged in safe places. Labs, ships, planes. Not in steel boxes. Driven across rough ground by scared men. Under fire. Hanna's first model used 2 gyros for backup. A sensible engineering choice that made a bulky system. Summer 1940 tests at Aberdeen showed promise. The gun stayed within 3 of elevation, while the tank moved at 12 mph over moderate terrain. 3 sounded precise, until you calculated what it meant downrange at 800 yd3 of elevation. Error meant 42 ft of vertical spread. You might hit the ground in front of the enemy tank. You might hit the sky above it. You probably wouldn't hit the tank. The system was too complex, too heavy, too slow to respond to the quick changes in vehicle motion. Back to the drawing board, the breakthrough came under pressure that would have crushed most engineering programs. December 7, 1941, erased every comfortable timeline. Pearl Harbor meant production schedules that had seemed aggressive now looked dangerously slow. The M4 Sherman medium tank made to replace the bad M3. Lee was scheduled to begin production in February 1942. Hanna had 8 months to deliver a stabilizer. System that worked, could be mass-produced, and wouldn't require a mechanical engineering degree to use 8 months to perfect what every military group in the world considered impossible. He abandoned the two-gyro approach entirely. Redundancy was an engineer safety blanket, but safety blankets added weight, complexity, and failure points. The solution that emerged was radically new, a single anticipating gyro that predicted gun movement before it happened, rather than reacting after the fact. Traditional stabilization worked like a man trying to balance a broom on his palm. Constant small corrections chasing the problem. Hanna's system worked like a man who could see the future half a second ahead and stop the broom from tilting in the first place. The gyroscope spun at 10,000 revolutions per minute, fast enough that its spin kept it from changing direction. Mount that gyroscope to the gun's elevation axis, and any up or down movement of the tank hull would try to tilt the gyro. The gyro would fight that tilt and make a signal that matched the disturbance feed, that signal into a hydraulic servo valve, and the valve could push a piston that moved the gun the other way, canceling the motion before the gunner could see it. The whole system weighed less than 300 pounds and hooked right into the Sherman's existing oil gear, hydraulic turret traverse system, pulling power from the same pump that turned the turret. The beauty was in the simple fit, no extra power source, no extra controls, just a black box between the gunners, hand control, and the gun. When the system was turned on, the gunner still aimed the same, but the gun stayed almost perfectly steady. Aberdeen proving ground tests in September 1940. One gave numbers that made even the doubters pause. Sherman's prototype with the stabilizer on target at 800 yards. Tank speed 12 miles per hour on a rough test course, 7 hits out of 10 shots. Same tank, same crew. Same course with the stabilizer off 1 hit out of 10. The change was not small. It was huge. Production started right away, and every M4 Sherman, except the one with the 105mm howitzer, got the Westinghouse stabilizer as standard gear. By August 1942, the 1st Sherman battalions were getting ready to go to North Africa, and each tank had the black box that ordnance officers had called a fantasy 18 months before. But a problem nobody had planned for showed up when the gear reached the crews. The technical manual for setup and operation was 47 pages long. The setup for the stabilizer needed a trained expert and about 2 hours of careful work. Oil pressure had to be checked. Gyroscope spin-up time had to be watched. Electrical wires had to be tested in the right order. One loose wire, one air bubble in the hydraulic line, or one wrong setting could make the whole system stop working, or even worse, fight the gunner's controls and make aiming impossible. Most Sherman battalions in the summer of 1942 did not have anyone truly trained on it. They only got a short basic lecture. The crews were draftees and volunteers who had been civilians 6 months before. They were still learning how to drive 32-ton tanks, load shells, talk on radios, follow fire orders, read maps and fix engines and transmissions and suspensions. Adding a tricky electric and hydraulic stabilizer was possible in theory, but in real life, it was too much to learn. In the short time they had, when the 1st Shermans arrived in North Africa, the crews saw the strange new controls next to the gunner's seat. looked at the big scary manual and made a choice that felt right. They turned the stabilizer off and fought the old way, stopping to shoot like every other tank crew in every other army. The British 8th Army got 252 M4 Shermans just before the El Alamein attack, and they did one important thing differently. Westinghouse sent experts to work with British repair teams to train them on how to use the stabilizer. It was not full training. There was not enough time, but it came straight from men who really knew how the system behaved. Some crews learned the steps and practiced them until the 27 actions became natural. Most ignored it, trusting old training over new machines. But a few tank commanders saw what the black box could do. And on October 24, 1942, that small group turned potential into deadly power. The British 9th Armored Brigade moved against German Panzer III and Panzer IV tanks. At 1,200 yards in the gray morning light, doctrine said, "Close the distance. Stop, engage." But the crews who used the stabilizer found something that changed the whole math they fired while still moving. At 8 miles per hour, and their shells hit the target. Not every shot the stabilizer could not stop all motion, and the gunner's skill still mattered, but enough shots landed to matter. German tank leaders trained to expect the stop, then shoot. Then, move pattern were caught in mid-routine. They saw the Shermans coming, began to stop, waited for their tanks to settle, started to aim, and then were hit before their gunners could get the crosshair centered. The Shermans fired first, and in tank fighting, firing first usually decided the fight. German after-action reports used careful words to note strange accuracy from American tanks, while moving, showing they did not understand. One captured Panzer IV crew told British intelligence, plainly, "We stopped to fire like we were trained. The American gun was already aimed at us." No German tank had this tool. The Panther would not enter service until mid-1943, and even then it had no gun stabilizer. The Tiger, known for its 8mm gun and heavy armor, turned its turret by hand when power failed, and it failed often needing 720 turns of a crank to go around. The Americans gave a capability the Germans thought impossible, and German engineers who looked at captured Shermans could not copy it. German industry had gyrotech, but making it work in a fighting vehicle under field conditions was different. That was Hanna's breakthrough, and it took more work than it looked. The numbers from El Alamein proved it. Sherman crews with stabilizers and training hit about 70% at ranges from 300 to 1,200 yards, while moving crews without stabilizers, following doctrine, hit about 8 to 12%. The gaps was not magic. It was 2 seconds. The stabilizer held the gun on target during the slow down when crews chose to stop and shoot in that battle now. They could pull the trigger the moment their vehicle stopped. The gun was already aimed at the enemy, so there was no delay for aiming. German crews lost 4 to 5 seconds getting their guns ready after stopping. They had to let the tank settle, line up the sights, and find the target again. In fights counted in heartbeats, those seconds were deadly. The United States 1st Armored Division landed in North Africa in November 1942 with more than 300 Sherman tanks, but the stabilizer was turned off in 80% of them. The reasons made sense to officers who had to get crews ready fast. The system was complicated. Setting it up needed careful calibration that field mechanics had not learned yet. In the Tunisian desert, sand got inside everything: engines, transmissions, turret rings, and delicate electrical parts all suffered. And that looked like trouble to veterans. Experienced tank officers who trained, the crews warned that the gear was too complex and might fail in these harsh places. They said it breaks too easily, and then you have a gun that will not aim at all. Removing the stabilizer would mean depot-level work, so most crews left it installed, but they kept the switch off. and the device gathered dust inside tanks meant to use it. The field manual that should have helped instead made problems worse. The manual showed the stabilizer in diagrams, but it treated firing while moving as a last resort, not a real tactic. Field Manual 1712, published in April 1943, after American tanks had seen 6 months of combat, said firing the 75mm gun while moving is inaccurate and wastes ammunition, and it should be done only in an emergency and at 600 yards or less. Crews read that and thought the Ordnance Department did not trust the system, so why should they? The maintenance. Problems turned doubt into full rejection. The stabilizer needed 4 things to work: correct hydraulic oil pressure from the turret pump, a gyroscope spun up to 10,000 rotations a minute, stable electrical power for the servo control, and exact calibration of the sensor that changed gyro signals into hydraulic moves. In depot conditions with trained technicians, setup was possible. But in the field with tired crews and sand and heat, it was a different story, and training time was painfully short. Setup was methodical, but in the field with mechanics who got only a half-day course, setup was guesswork. One air bubble in the hydraulic line made the gun move badly. One corroded electrical connection made the servo fight the gunner. One wrong sensor setting made the gun hunt up and down trying to find steadiness. When crews saw these failures, word spread fast through battalions like survival. News people said, "The stabilizer is junk. Turn it off before it gets you killed." No one blamed the short training or rushed maintenance. They blamed the new machine. The worst results showed up at Kasserine Pass in February 1943, when American armor met German panzer forces in the first big fight. 183 American tanks were lost over 4 days. Many failures came from poor unit coordination, bad scouting and defensive positions, chosen without thinking about fields of fire. But a technical failure no one knew about also mattered: American Shermans, with stabilizers off, followed stop doctrine against German tanks doing the same. The fights came down to crew training, tactical position, and weapon performance. In those areas, experienced German crews with better optics and longer guns had the edge. German after-action reports praised the mechanical reliability and good ergonomics of captured American tanks, but said enemy crews stopped and fired as expected. Standard rules still worked. The Americans had brought a secret weapon and never unwrapped it. The turning point came from one curious and obsessive leader, Lieutenant Joseph McCoy of the 26th Tank Battalion, 66th Armored Regiment, 2nd Armored Division. He spent the Atlantic crossing to Sicily, reading the Westinghouse manual cover to cover, not skimming. He learned the calibration steps and memorized the troubleshooting charts, while others played cards or slept. McCoy drilled his crew on stabilizer, set up until the 27 steps were automatic. Verify oil pressure reads 180 to 220. PSI engage master power switch. Wait for gyro spin-up indicator. Check servo response with a test displacement. Calibrate 0 point with gun level, engage stabilizer. Clutch verify gun holds position during fake motion. His gunner could do the sequence in under 10 minutes without reading the manual. Other platoon leaders mocked him quietly. McCoy is wasting time on that contraption. Wait till the first breakdown. Then we'll see. The Gulf Beach Head, on July 10, 1943, gave the lab German Panzer IV tanks counterattack the Allied landing zones in the kind of mobile fight that doctrine said favored the defender. German crews knew the terrain had prepared positions and could use maneuver to offset number disadvantage. McCoy's platoon advanced with stabilizers engaged, and he briefed his crews on something the British had learned at El Alamein. You didn't fire on the move for accuracy at long range. You fired on the move for two reasons: suppression and preparation. Suppressive fire kept German crews buttoned up, reluctant to expose themselves to spot accurately. It hurt their ability to coordinate and maneuver. It wasn't about hitting them at 800 wide while moving. It was about forcing them to respect your fire while you close distance. And when you reached 600 YAD and made the decision to stop and deliver a killing shot, your gun was already on target. No aiming delay. Crosshairs, exactly where you'd left them. Squeeze trigger, absorb, recoil, fire again if needed. The German crews went through their practice sequence: stop, vehicle, wait for settling, center sight, picture, acquire target, aim, fire. By the time they completed that sequence, McCoy's gunner had already put a round into their hole. The word traveled through 2nd Armored Division like electricity crews who mastered the stabilizer gained 3 to 4 critical seconds in every engagement. It wasn't about big tactics or big battlefield miracles. It was about cutting aiming time to zero when you stopped. The gyroscope held the crosshairs exactly where the gunner had placed them, 30 seconds earlier before the tank started moving before terrain. Intervened before anything changed, stopped the tank, and the gun was ready. No searching for target, no compensation for movement, just fire. The U.S. Army Ordnance Department, stung by Kasserine and confused by mixed field reports, ran formal tests at Fort Knox in summer 1943 with controlled conditions and careful measurements. They published the results as simple bulletins that reached every armored unit. Crews with stabilizers and proper training cut time to first shot by an average of 2 seconds compared to tanks without stabilizers. Chance to hit at 800 yards rose from 45% to 68% for trained stabilizer crews in controlled tests. In real combat, where stress lowers performance, the gain was smaller, but still real. Properly trained crews averaged 55 to 60% hits, while conventional crews averaged 30 to 40%. The data quietly changed doctrine. The next printing of Field Manual 1712 would add new advice on using stabilizers, but thousands of crews were already fighting, and headquarters changes did not change what men believed in the field. The stabilizer had a bad name from early failures and weak training, fixing that cost proof in blood and survival. The Normandy. Bocage showed the stabilizer's value in terrain the manuals had not expected. The hedges of northern France, with thick earth banks and old trees, made natural walls between small fields and turned tank fights into knife fights under 300 yards. Visibility was a few vehicle lengths, and fights lasted seconds. German crews dug-in positions with clear lanes had every advantage of position and preparation. This proof changed training slowly, as men learned by doing and surviving battles. 2 American Sherman crews moving forward through the Vosges needed every technical advantage they could find. By June 1944, enough crews had been trained to use the stabilizer, so the system finally worked the way it was meant to on the battlefield. The use was very practical when a Sherman took fire and had to back out quickly from a dangerous spot. The rough rocking motion from moving backward over uneven ground usually made aiming impossible. Crews using stabilizers could shoot while moving. Backward, the gyroscope kept the gun steady through motion that would have ruined any normal aiming. Crews described the effect in the plain way men talk about tools that kept them alive. We can get 2 aimed shots off while reversing before the 2 German tank can fire. Once that is the difference between getting back to cover or burning in the lane. The stabilizer did not remove all danger. Nothing could in terrain that gave the defender such an advantage. But it made the time you were vulnerable much shorter from deadly to survivable. The full advantage of American tank design showed in these close fights, where many technical features worked together to give tactical superiority. Sherman turrets could turn 306 CT in 15 seconds using electric. Hydraulic power that meant 20 meters per second of smooth controlled movement. A gunner could follow a moving target continuously. The turret could keep up with the threat, while the stabilizer kept the gun steady in elevation. German Panther tanks were famous for their sloped armor and strong 75mm L-70 gun, but their turrets turned in 18 seconds at high speed. The power system was often unreliable and could fail from battle damage or mechanical problems. When power traverse failed, Panther crews had to turn the turret by hand at 36 axion per crank. That meant 720 full turns to make a 360° rotation in close fights. Where targets appeared and disappeared quickly, a Panther with broken power traverse was like a pillbox with great armor, but a gun that could not follow the enemy. The German Tiger I, the heavy tank that scared Allied soldiers and was praised in German propaganda, took 60 seconds to turn its turret all the way at low engine speed. The hydraulic system got power straight from the engine, so turret speed depended on engine speed, and idling Tigers turned very slowly. American crews learned how to use this to their advantage. Force the Tiger to turn, then move sideways faster than its turret could follow. The Sherman's 20° per second turn speed meant American gunners could stay on target while German crews struggled to keep up. Add the stabilizer to that, and the gun stayed steady while the Sherman moved ready to fire the moment the crew wanted, and these technical advantages added up to tactical dominance. Exactly in the kind of close, fast fights the Voyage demanded, the news spread through armored units as crews shared notes and survival numbers. Platoons trained on stabilizers reported higher kill ratios and lower losses than normal platoons in the same battalion fighting the same enemy. The proof was not official, but it was convincing. Crews who trusted the system lived longer, even when German guns were stronger, and the Panther's 75mm L-70 could pierce Sherman front armor at over 1,500 yards. American crews often fired first because they reached firing position faster. The stabilizer kept the gun on target, while moving the power traverse followed the enemy. The gunner pulled the trigger when the angle was right, and the German crew was still aiming when the American round hit. German tank crews captured and interviewed said again and again they could not understand how American fire was so accurate. American turret control let them fire fast, one Panther commander said. In a detailed report, crews could fire correctly with almost no stopping time. We must assume the first shot advantage belongs to the enemy. German engineers studied captured Shermans. They took photos of the stabilizer parts, measured the gyroscope, and traced the hydraulic lines. They reached a conclusion that proved Hanna's 18 months of careful engineering worked. The system was too complex for field production. In Germany's stretched industrial system, the gyroscope needed exact manufacturing, the servo control unit needed special electrical parts, and the connection with hydraulic systems needed careful adjustment. Germany could build the parts, barely, but could not make them in large numbers with the reliability needed for combat tanks. The stabilizer needed an industrial base that could make precise instruments by the thousands, and trust they would work right without individual tuning. Germany's artisan style of tank making, where every vehicle got personal attention and adjustment, could not match the mass production precision. The American system expected. A captured German manual from Panther crews in August 1944 gave tactical advice that accepted defeat without knowing why. American tank turret control lets crews fire fast. Crews can shoot accurately with almost no stopping time. Assume the first shot advantage is with the enemy and make up for it with better position and smart use of terrain. The Germans changed their tactics to fight an advantage they could not match with technology relying on panzer skills and smart positioning. It was good practice against a better system, but it gave up the initiative by September 1944. American Sherman production reached 200 tanks every month, and every tank came off the line with the Westinghouse stabilizer as standard equipment. The setup steps were made easier with field feedback and engineering improvements. What took 12 hours of technician work in 1942 now took 4 hours of crew work in 1944. Fort Knox training courses spent whole days on stabilizer use, with instructors who had survived combat teaching the system not as complex tech, but as life-saving tools. Crew training went from 15% in 1943 to 60%. By fall 1944, hit rates for crews trained on stabilizers reached 72%, at fighting ranges of 300 to 1.0 yards in clear conditions with trained gunners and well-maintained equipment. The Edge Clinton Hanna had built in a Westinghouse lab was now standard equipment in the most produced tank of the war. It was so well integrated that crews saw it as normal, not something new. The stabilizer's best time lasted from D-Day through fall 1944, when American tanks faced German tanks that were individually stronger but were outnumbered by American numbers, logistics, and combined technical advantages that gave battlefield control. The Sherman was not invincible, far from it, but it was fast, reliable, and, in the hands of trained crews, deadly at the ranges where most tank fighting actually happened. The calculations that seemed impossible in 1939 were now normal: fire while moving, hit while moving, survive while moving. Wars are not won by one invention, but by patiently using many advantages until the enemy runs out of answers. The reckoning came in fall 1944, when American crews faced the hard math of armor penetration versus armor thickness. The stabilizer gave exactly what it promised: first shot advantage by faster aiming and less time to get on target, but against German Panther tanks with front armor 120 meters thick at 55 Meter slope, and Tiger tanks with front armor 185 millimeter thick. First shots were not always enough if the shell bounced off harmlessly. The Sherman's 75 mm M3 gun could pierce Panther front armor only under 300 yards, with perfect straight hit beyond that crews had to aim at side armor, turret rings, or tracks. Precision shots that needed skill, courage, and luck. That combat rarely gave the stabilizer made crews faster, but not invincible. And the battlefield showed that clearly. The Battle of the Bulge in December 1944 gave the full test. Sherman battalions with fully trained stabilizer crews showed how much difference proper training and technical advantage could make. Crewsmen who survived Normandy and fought across France, who knew their tanks inside, out, and trusted them completely, reported first shot success of 65% against German tanks. The stabilizer worked as it was meant to. Crews found targets faster, aimed faster, and fired faster, but getting through heavy German tank armor told a different story. Only 22% of hits killed Panthers and Tigers, hitting them from the front. The stabilizer gave the advantage. It was designed to give. It just could not beat the laws of physics. Impact power depended on projectile weight, speed, and angle. The Sherman's gun fired a 15-pound shell at 600 feet per second. The Panther fired a 15-pound shell at 100 feet per second. That speed difference made a big difference in penetration, and no aiming system could fix that. American crews used tactics that made the most of what they had. Mobility kept them alive. Shermans were faster off-road than Panthers, more reliable than Tigers, easier to repair and recover. When damaged numbers counted for a lot, for every Panther. Germany made America built 5 Shermans, and the supply system that kept them fueled, armed, and working never failed. And the stabilizer still mattered, because most tank fights happened under 800 yards against targets, other than heavy tanks. German Panzer IVs were still the main tank in panzer divisions, and against them. The Sherman gun was good against towed anti-tank guns, fortified spots, and infantry. The Sherman was excellent. The stabilizer made all these fights faster and more deadly, even if it could not make a 75mm gun act. Like an 88, the 76mm A1 gun came. In late 1944, as the Army's answer to the penetration problem and Sherman's with the longer gun got improved, stabilizers adjusted for the new gun's recoil. These crews reached 70% hit rates at over 1.00 yards while moving 12 mm, showing how effective the system and training were together. The advantage was unmatched by any other army with tanks in large numbers, but production came too late to replace most Sherman battalions by the end of the war. About 30% of Shermans in Europe had the 76mm gun. The rest used the original 75mm, making up for it, with crew skill, smart positioning, and the reliable systems that worked when everything else failed. Human stories cut through numbers with the clarity of real experience. Sergeant Jim Bates' 4th Armored Division wrote home in March 1945 in a calm tone of a man who survived long enough to know what kept him alive. Our tank is not the strongest. Everyone knows that German Panthers have better armor, bigger guns, all the technical advantages. But when we roll into a fight, we shoot first. Every single time. The other guys are still turning their turrets, still setting sights, still trying to get their guns ready. And we are already firing that black box under the gunner's seat. The thing everyone said was useless. Back in training is what keeps us alive. I don't care what armor charts say. I care that my gunner can fire 2 seconds faster than theirs. And in this fight, 2 seconds is everything. The final numbers told the story that single battles hid of 49. 324 Sherman tanks made between 1942 and 1945. About 47,000 had the Westinghouse stabilizer as standard gear crew. Training reached 60% by the war's end. Up from 15% in early 1943, tests showed an advantage of 3.8 seconds faster to first aimed shot versus tanks without stabilizers in real combat with rough terrain, low visibility, tired crews, and worn tanks. The real advantage was smaller, maybe 2 to 2.5 seconds, but still enough to make a difference. Tank fighting at normal ranges. Tank fights lasted between 12 and 30 seconds from the first sighting to the end of the fight. Firing 2 seconds sooner meant getting off 1 more aimed shot, sometimes even 2 in fights, where both sides had clear shots, and enough ammo the crew that fired. More aimed rounds, faster, usually won. The stabilizer did not promise victory, but it made winning more likely and saved lives. Clinton Hanna got no medals for his work, no battlefield awards, no public recognition beyond technical groups. The Army Ordnance Department sent a letter in April 1945, typed on official letterhead in the formal style of organizations that notice success without emotion. The gyroscopic gun stabilizer has proven very valuable in combat operations. Crew acceptance has grown a lot after better training programs. System reliability in the field was better than expected. Continued development is recommended for post-war tanks. The letter stayed in Hanna's desk drawer for decades, a small proof of 18 months of focused engineering and 5 years of watching reports that swung between success and rejection. He had made a system that did exactly what it was supposed to do, kept tank guns steady while vehicles moved over rough ground up to 15 mil baptimeter. The fact that crews at first rejected it, that rules lagged behind the technology, that training failed before hardware did, none of that took away from the engineering achievement. He had solved the problem everyone said could not be solved, and eventually, the people who needed it most learned to trust it. After the war, German panzer crews interviewed said the same things. American intelligence analysts found both pleasing and worrying. American tanks fired with strange speed and accuracy. One Panther, commander said through a translator, "At first, We thought it was better training, better crews, maybe more practice. When we looked at captured Shermans, we found mechanical systems we did not understand, gyroscopes, hydraulic controls, electrical servo. Parts, we thought it was part of aiming, but the integration was too complex to figure out. In the field, our engineers never explained it to us. We just learned to expect American tanks to fire first, and we changed our tactics. They never understood the mechanical advantage because you had to see the whole system working all together, kept up and used by crews who trusted it. Captured tanks only showed the parts, not the full system. The victory was not in the parts. It was in the careful use of precise engineering to solve a problem everyone else had given up on.